This is a really well put together session, Brian, because Stacy's work on identifying trends and attributing trends to causes in the historical record, along with Tim's exhortation to embrace uncertainty and the use of confidence limits, and then Jared's background of the limits of what we can do or can learn from climate models leads into perfectly what, and that's not an accident, I guess is my point, thanks Brian, what we're trying to do with this NCHRP project. Before I get too far into it, I want to acknowledge the rest of the team that's working on this portion of it, which is what I would refer to as the inland hydrology portion. We have an interdisciplinary team of engineers, hydrologic engineers, including myself, as well as a team of climate scientists. And they're listed here. Will Thomas is here with us in the audience. Several other engineers, Rudy Herman, Sabu Paul, Jennifer Jacobs, and Dave Thompson. And then we have 3 climate scientists as well, Catherine Hayhoe, who Jared mentioned, and Ann Stoner and Chris Anderson, who have all contributed to this. And believe me, we have a lot of lively discussions with this project in terms of balancing the needs of science with the needs of engineering. So here's the title of our project. Applying climate change information to hydrologic and hydraulic design of transportation infrastructure. So what do we do with all that information that we've been hearing about? Are there trends in the historical record? Are there not? How do we understand them? What do we do with uncertainty? And what can climate models really tell us? Because engineers are out there designing, maintaining, and refurbishing infrastructure that costs millions and millions of dollars every day, and it's going to be out there in the future. And so we need tools. I would argue that we need tools today, even though we have those uncertainties. So that's what this is about. Our objective is to come up with design tools that can be used by engineers. So there are 3 questions that I want to ask that really set the stage for this whole process. First of all, what about our current methods? What are the weaknesses in those current methods? And I've listed not weaknesses, but the 3 types, are the way I categorize them in my mind, is the rainfall runoff models, statistical methods, and more empirical methods. And what I'm going to talk about today is, and the project has a larger scope to it, but what I'm going to talk about today is those methods that require precipitation as an input. So if you do a hydrologic analysis that requires precipitation, that's what I'm addressing. But there are weaknesses. Stationarity is one of the problems that have been identified, but we already know that various of our methods have limitations that we live with, because in the engineering world, that's the reality. The second thing is, and Jared touched on this, how reliably can we predict what the future is going to look like? We're not talking about trying to predict when the next Hurricane Sandy is, but what is the climate environment going to be by the end of this century? What do we know about that? And then finally, how will we use uncertainty? Even though we have a lot of historical records, we don't even look to the degree that I think we should look at the uncertainty in our existing records. And I have a few comments about that near the end of my talk. So 2 things I like to keep in mind as we've gone through this process with this project. One is that all models are wrong, but some are useful. And that's a quote from George Box, I believe. He was the first one that attributed it, recognizing that what we come up with is not going to be ideal. There's always going to be an improvement. Scientists will always be able to think of other details that we can incorporate into the process-based, the physically based models. But just like our current engineering tools, they're not perfect, but they are useful. And if they're not useful, then we stop using them. The second thing is not to let the perfect be the enemy of the good. I think that was first attributed to Voltaire a long time ago in some poem or something, but we're not striving for perfection here. We're striving for something that's useful, something that can help us direct those infrastructure expenditures that we're doing every day. So that's background in terms of how I couch what we're trying to do in this project. Now, 2 of the challenges that I want to talk about are in the next 2 slides. And the first one is how we estimate extremes, which Jared was talking about. Engineers typically are interested in very extreme precipitation events. I'm using the 24-hour precipitation as an example in this graph, where we want to know what the 100-year 24-hour is, what the 10-year, what the 25-year. When I'm talking about extreme, that's much more extreme than what a climate scientist is talking about typically, where they might be talking about the 99th percentile of all daily precipitation events. And as we know, that the extremes in this distribution are very, very sensitive to what distribution we choose. So there's a lot that goes into that. The second challenge that we have is related to subdaily. And again, Jared touched on the difficulties in going to the subdaily. Even if we know what the 24-hour precipitation is for a given return period, how do we go about getting lesser precipitation durations for the same return periods? So that's what I want to talk about for the most part with my time today. Now, I'm not a climate scientist myself, but you got a good overview of climate modeling. I have it in a framework from a presentation that Catherine did, where we start with these scenarios of human activities. And down in the bottom in the center there, you see four. Jared mentioned the RCPs that range from less severe to more severe. And they're based on how much carbon is in the atmosphere. Then we move into the global climate models that Jared talked about, and then we move into downscaling. And as Jared mentioned, there are two different types of downscaling, the dynamical or regional climate modeling and the statistical modeling. That gives us on the right-hand side there our high-resolution climate projections, and that's what I'm focused on, how we use those high-resolution projections. Here is a graph that shows three of those scenarios in terms of the global mean temperature. And climate scientists tell us that they have a much higher degree of confidence. Jared just told us this too, with temperature, and then they do with precipitation. And this is an example of the different temperature ranges that there are associated with those three RCPs. Some of the points that I want to make with this is that in the near term, in the next 30 years, you can see that there's not that much difference between them. So if you're talking about infrastructure that has a very short lifetime, you probably don't need to worry so much about climate change. But if you're talking about something that has a much longer lifetime, like roadways and bridges and much of the infrastructure that we work in the transportation field, we will need to be more concerned with that. So the last bullet there on the right-hand side is we want to look at as many of these climate models as possible. They all have physics-based representations, so you might think they should all agree, but they don't because they have different starting conditions. They have different resolutions, both temporal resolution and spatial resolution, and so they come up with different answers, and we can use those answers as ways of building confidence limits around the estimates that they may be making. So one of the things that we look at in our project was, well, what data set should we go to? And we've developed a number of different tools, including this table, in describing several different high-resolution data sets. In terms of Jared's talk, the two right-hand columns are related to the dynamical downscaling and regional climate models. The other three on the left are statistically downscaled. And we looked at a number of different things, including how many scenarios they included in their analysis. We looked at what the time steps were. You can see that all of these are daily, except for one of the regionally downscaled data sets has 3-hour data available. We also looked at the spatial resolution, smaller being better in general, and you can see variations there. And we came up with a recommendation that for most uses, we want to point people towards the local data sets. Now, one of the things that I want to emphasize from Jared, too, is that in terms of his over-the-counter analogy or specialist, we have incorporated, as HEC-25 has for the coastal environment, a series of levels of analysis from 1 to 5. And as you go up in level of analysis, you're probably going to need to move from the over-the-counter to the prescription. This is just one slide I want to show from some comparisons that Catherine Hayhoe performed on some of the limits in representing extreme precipitation. This shows precipitation biases for 3 different levels, from the 10 percentile, the 50 percentile, and the 99th percentile, and that's of daily values. So again, the 99th percentile is not extreme at all. But to the extent that you see color in there, the more color you see, the more the bias is. And so you can see that, especially in the quantile mapping, the modeling is very, very good at the less extreme quantiles and less good at the more extreme quantiles. So how can we deal with this, or what are the recommendations that we're trying to work through? And these are preliminary. We have a panel that we're working with, and we're still in very active discussions with them. But one of the things that we can do is we can wait for the downscaling GCM output to get better. Jared was talking that it is getting better, but it's not there yet for many of the applications. And considering that we're putting more and more infrastructure in the ground, that's probably not a good option. A second option is to wait for the development of more programmatic tools. 2 of the ones that we've looked at in this study are the ones that Jared mentioned, and that's the New York work and the Canadian work. And we actually have a preference for the Canadian work for various reasons that the report describes. But unless you're in Canada or in New York, those tools aren't yet available for you. So what we're focused on is coming up with a methodology for estimating extreme 24-hour precipitations based on a 10-year value, and then scaling up to the 100-year or to the 50-year or whatever value you want to. But then the problem with that is if you're scaling up based on existing relationships in the flood frequency curve, then you are assuming stationarity, because you're assuming that the existing relationships hold true in the future. And that we want to avoid as much as possible, but that may not be the worst thing to do. In fact, I think it's a reasonable thing to do in most cases, because, as Jared pointed out so well, there's a lot of uncertainty associated with the ability of the climate models to represent extreme events. And so we have one limitation of avoiding stationarity, another limitation of what the climate models can produce for us, and we need to balance those 2 to come up with workable tools. So basically, what we have now in our work is proposed a 10-step procedure for coming up with a 24-hour design storm. It uses a lower and a higher scenario so that you get a range of outputs that you can look at in your design. It uses multiple global climate model outputs so you can compute confidence limits, so you can get a median estimate of your 24-hour precipitation, and you can get a higher, a 90% confidence limit, for example. And then, as I say, it indexes to the 10-year event. So just by way of a simple example, this is a table of an output from NOAA Atlas 14 for a particular location in Denver, Colorado. And I've circled the 24-hour values there, and I'll put that up closer. 3.6 inches, along with the you'll notice the confidence limits below that. 3.6 inches is the 10-year 24-hour precipitation in this location. 4.76 inches is the 100-year location. So what I mean by scaling, simple scaling up, is to compute an index. So 4.76 times what? Or divided by 3.6 is 1.32. So there's a ratio in the current flood frequency curve of 1.32. And so the argument is that we can better predict a 100-year because of the limits in climate modeling from estimating the 10-year, which is not quite so extreme, and then using the relationship historically between those 2. So we would estimate what our 10-year event is and then multiply that by 1.32 if we want the 100-year, for example, as opposed to trying to use the same curve fitting techniques for the 100-year directly, because again, we're further out on that extreme tail and we're in more dangerous territory. Now that does assume stationarity, but it avoids the limitations that we were talking about related to downscaled GCM output in estimating the extremes, and it is site-specific. That ratio of 1.3, for example, is good for Denver, but we would get a different number for any other location. And so why the index approach? Well, I've kind of explained that already, but the extremes are very sensitive when we're talking about either the partial duration series or the annual maximum series. We have limitations in the climate outputs related to the physics that they may or may not include, talking about the way they represent thunderstorms or hurricanes and how that moves down through the downscaling process. And then the spatial representation can also average out information as well. And so using the historical flood frequency curve, which has good information in it, seems like an appropriate way forward. Now the second part is, what about subdaily precipitation? As Jared described, it gets murkier as you go subdaily. Again, we can wait for better modeling. Jared better get on it right away. We can wait for other programmatic tools, and the Canadian tool and the New York tool are examples of that. Or we can use the scaling approach again for subdaily. And so you can say, well, no, we don't want to use stationarity, but we're trading off stationarity with the limits of what the climate modeling is allowing us to do. So here's that same table. Now I'm looking at a column in that table for the 10-year event, and I've got all the subdaily values that I've copied over to this table. And then the right-hand column is then that ratio. The 24-hour is back to that 2.89 there that's highlighted in red. And so I get ratios on the right-hand column. So for example, the 60-minute is 46% of the 24-hour. And then I can then estimate, you can see in the right-hand column in this table, I've estimated that my 24-hour under a future condition is 3.18 instead of the 2.89. And then using those ratios, I can estimate my 60-minute duration, my 120-minute duration, any of the durations, and create my new curve. Now here's where I want to put it into the context of that uncertainty that Tim was talking about. Here's an example of a 10-year IDF curve. Actually, there are 4 of them there. 3 of them are the existing NOAA Atlas information based on the median values, or the mean values, and then the 90% confidence limits. And then you can see the dashed red line is the projected value, and it's within the confidence limits in this particular case, within the confidence limits for this scenario. And so if we're serious about understanding what this uncertainty is in the existing data, maybe we're not so concerned for this particular site about what the future is going to be if the data, or if the projected information looks like this. So the last thought I want to leave you with is something we developed in HEC-17 that we're still carrying forward with, and that's a climate change index, which is intended to be a measure of how concerned you should be about your precipitation changes. So what I'm showing here is just a probability distribution of 24-hour precipitation, and that's the existing, we'll just call it the NOAA Atlas 14 value for the 24-hour precipitation for a given return period. And with NOAA Atlas 14, we have the upper limit, which is shown there, and the distance between those two I'll label B. And then using that 10-step procedure I mentioned earlier, you can come up with a projected value of precipitation using our global climate modeling output. And the difference between that and the existing I'll call A. And I like simple things when they are useful. So the climate change index is simply A divided by B. And what we say is if that's small, then probably if you just look at the uncertainty in your existing information, you'll be doing just fine in evaluating your design. But if that number is large, then you might want to go away from the over-the-counter solution and move towards the prescription. You might want to include a climate scientist in a more detailed analysis. You might want to do a whole host of things that we talk about in the draft guidance. So with that, what we're trying to do is come up with practical methods that we can use now because we're spending money now. The science is not perfect, but it is available to us and useful. What we've recommended is that for most cases, you look at the LOCA data set. I didn't say what that stands for, and I'm not going to. Localized analogs, I did it. And we use a range of scenarios, and we're talking about a lower scenario, RCP 4.5, and a higher scenario, 8.5. We're recommending, at least tentatively, that you look at a moderately extreme event to try to estimate that using the 10-step procedure for a 24-hour. And then for higher values, go ahead and stick with the stationarity assumption to scale that up to 100-year or 500-year or 25-year. For the subdaily, use the estimated 24 and scale it down to shorter durations. And I don't want to leave you with the impression that this is the only thing that's in our recommendations. We have several more complex methods that we do recommend. But again, this is for the common situation that we think most people are going to be using most of the time. And then I just want to leave those quotes up there. All models are wrong, but some are useful. And let's not let the perfect be the enemy of the good. And so that's where I'm going to stop now, and I'd be happy to answer any questions.
Okay, so we've got a working mic now, so question in the back?
Yeah, did you compare and maybe I just missed it, but when you ran the Colorado data and got the 10-year events increased for the global climate modeling, did you compare that to the 90% confidence interval that's in NOAA Atlas 14 to see where it falls in that range?
That's what this graph was. So if you look at the 24-hour value there, that's what we indexed on. That upper curve, I guess I need to turn my, get this on. So that upper curve is the upper confidence limits from NOAA 14. That is the lower confidence limit from NOAA 14. That's the mean. And then that's the projected climate value. Anything else?
What is the stationarity assumption? Like, what's being assumed for that?
What the stationarity assumption comes in the ratios here. So these are the existing ratios in the case of the subdailies. So for example, that the 30-minute precipitation is 0.37 or 37% of the 24-hour. So in going from, here's my projection from 2.89 is my existing NOAA Atlas value. 3.18 is what I get out of my 10-step procedure for the projected climate information. And then the stationarity is assuming these ratios are still true in the year 2100, which that's a big question. In terms of Stacy's quotations on the many reports about science and being science-based, we don't know what stationarity is going to look like. We know it's worked for us in the past, but we haven't yet. So we're assuming that it's still valuable to us going forward because we don't have a better option until we get these climate guys and gals working, getting more detailed models.
So we throw a lot of terms around, stationarity, non-stationarity. Are these terms that are new to people? Do we need to define stationarity and non-stationarity just for dummies like me?
Well, stationarity, I think Stacy gave a good definition of it. Stationarity meaning the relationships between our climate variables that have gone on in the past is going to be valuable in the future. Whenever you do a log Pearson analysis of gauge flows and you're estimating your 100-year, you're assuming that the gauge flows that you've measured in the past are representative of what's going to be happening in the future. Non-stationarity that's not true.
So just to expand on that, since the emphasis is that we're assuming stationarity, is there consensus among the climate science community that with these models for the 24 or daily precipitation that we do have non-stationarity then?
Well, I think Jared expressed it that, for example, the various examples that he gave in terms of hurricanes slowing down, storms intensifying, the physics are not changing, but the conditions within which the physics work causes changes in these storms. I don't know if I said that right. So the physics aren't changing, but the relationships between those things are changing. And a very simple example for any of you who work with rain on snow or precipitation coming down in different forms. If you've got changing temperatures, then you're also going to have changes in the storm mechanisms that may be driving what your 100-year flood is or what your 25-year flood is. So in terms of these recommendations, we're not assuming stationarity when we're talking about getting the 24-hour precipitation, because we believe that the 24-hour precipitations and the climate science community supports the notion that those are reasonable representations, but the subdaily are not. And so you're left with trying to do statistical analyses on 1-hour storms, which is probably not valid with the current state of climate modeling.
Okay.
Yeah, I'd add that the Weather Service is, in their process of updating NOAA Atlas 14, they're also looking at trying to identify any kind of trends in subdaily precipitation. So that stationary assumption may not be valid, but the Weather Service is trying to determine how invalid or valid that assumption is.
Another point I wanted to make about stationarity is that, and Jared said this too, statistical downscaling assumes stationarity in the relationship between the historical record and the projected record. So climate scientists that work in statistical downscaling routinely use that tool in downscaling to spatial scales that those models work with. The regional climate modeling gets away from that. It has biases associated with it that need to be corrected in some way. But one of the reasons I put this back up is you can see that currently there are a relatively small number of data sets that are available, both in terms of the numbers of scenarios and the number of models. And so that's another one of the trade-offs in which data set that you want to look at.